Hey there, I'm Nix, and the topic of today's video is solving the longest common prefix on the LeetCode website. As always, solving this problem in the C++ language and giving you a detailed explanation of the entire process, through the planning of the algorithm, to the coding of it, to the analysis of time and space complexities, as well as looking at LeetCode rankings. If that sounds interesting to you, then stay tuned. Welcome back, and let's get started. We want to write a function to find the longest common prefix string amongst an array of strings. If there isn't one, then we just return an empty string. And we have handy-dandy examples here and some constraints to pay attention to. First example here, we've got 3 words. Each of them begin with the letters F and L, so that's the longest common prefix. As soon as we get to the third letter, 2 of them have O, but the third one has I. That's a mismatch. That doesn't count. In example 2, every single one of them begin with a different first letter, so there's really no common prefix at all, and thus we return an empty string. For constraints, the vector is going to have at least one thing in it, but the strings it contains could potentially be empty, which is something to pay attention to. In addition, the vector strings can only consist of lowercase English letters, which is nice because that means we don't have to pay attention to how to handle things like spaces. Now that we know all of this information, how do we solve this problem? Well, I'm going to show you 2 different ways to do it. One way involving essentially going in reverse and using the erase method that's in the string class, and the other one going forward and using concatenation instead. First up will be erase. Now, a variable that we need to create is, well, obviously the string that's going to hold the prefix, if there is any. So we need to make a string that we could call prefix. So we make that string, and we can set it to whatever the first string in the vector is initially. Then we can start looping through the vector. And the very first thing we want to check is if any of these strings is an empty one. As soon as we find an empty one, we know that there can't possibly be a common prefix. So, in the case that we find one, we can just return an empty string. If that check passes, then we can go into another loop and look at each character in each string. And if we find a mismatch, then we know that our string containing what's going to be the prefix can be chopped away and eliminate all of the characters it has from that mismatch to its end. So as an example, comparing flow to flight, we get a mismatch in the third character here. So we know we can eliminate everything from that third character onto the end of the prefix. And in this case, it gives us the correct answer. Another thing that we have to check if we're using erase is if our prefix size is bigger than the string that it's comparing itself to. If it is, we know that we can eliminate everything from that string size to the end of our prefix string. And then after we've gotten through those nested loops and have looked through everything, if we've never found a mismatch and never entered that condition, well, then we know our prefix should be sorted at the end, and we can just return prefix. So going over those key points, let's move on to actually coding that out. First up, creation of variables, and the only variable we need to create is the string, and I've aptly named it prefix. And I've set it to the first string in this vector of strings that we're being given. Now is when the for loop starts. In the for loop, we start in index 1 this time because, well, index 0 has already been assigned to prefix, so we don't need to start there. We go until the end of the vector of strings and iterate each time. And the first thing we do, again, is check to see if that string that we're looking at has a size equal to 0. If so, that's an empty string, and we just want to immediately return that empty string, since no prefix is possible that's common to all of the strings present. Now is when we're starting to go into the second for loop. J equals 0, start at the beginning, we go until the end of each individual string that we're looking at. So we're looking at each character in that string. First thing we want to check if that character that we see in the prefix string is not equal to the character in the string that we're looking at, well, then we know we need to do an erase. To use the erase function, call the string .erase, and for this one, I want to erase a set of characters from one position to another. And the way to do that is by using iterators. So here, I want to erase everything from that J position on. So to do that via iterators, you indicate the beginning iterator, prefix.begin, plus J, and that will move it to the correct position. And then you want to erase everything up until you get to the end. As soon as you do that erase function, you'll want to break out of this inner for loop and start looking at a different string. Another thing you want to make sure to check is if your prefix size is bigger than the string that you're looking at, then that's also a condition where you need to do an erase. And this erase is going to erase everything from the end of the length of that other string to the end of the prefix. And to do that via iterators, you do prefix begin plus that string size, and you go all the way to the end. This if statement is a way to protect against the additional cases where you still have to chop away extra characters in the prefix, but you don't technically have a mismatch yet. And that situation could be seen in the example, say, instead of flower, flow, and flight here, what if we just had flower and flow? Well, the prefix would be set to this first string. The second for loop here is only looking at the size of the string that we're comparing prefix to. So we go until we reach the end of this string. And we've seen, hey, everything matches up to the end of this string. We're good, right? No. So this second if statement would be the way to chop off the E and the R in that prefix string. And as you exit the for loops, you now have the correct prefix. If this wasn't there, you'd get a wrong answer in that situation. The last thing to do is simply return prefix. As once we've gotten through all of these nested for loops, if we haven't gotten into this if statement, then our prefix should be correct, and we can return it to get the correct answer and hopefully green text when we run it. So let's see if that's the case. Pending, judging, green text. Excellent. And as we expected, we get F and L in this example. If we do a custom test case here and we say delete this, it should run, pending, judging, and we should get an empty string thanks to this if statement here. Alright, let's go for the full shebang. Pending, judging, and green text. Excellent. Now, let's look at time and space complexities. This string is a variable, so we're going to have to carve out enough space to be able to hold it. So it's going to be set to a size that's equal to whatever the size is of that first string in the vector. And it's only going to get smaller than that as the erase function goes on. So at maximum, while this method is running, it's going to be equal to that size, whatever it is. At the end, prefix is going to have a size equal to, well, whatever the common prefix is. And that could be anything from empty to, well, if we hit the jackpot and we get this first string being equal to exactly what it's supposed to be at the end. Now we can sum up that and say that the prefix is equal to whatever the largest common prefix is, and we call that n. So this is going to be equal to a big O of n space complexity. For time complexity, well, we have a for loop here, we have a nested for loop within it, and we have the erase function that we're using. All of those have some time dependencies we need to take into account. This first for loop is dependent on the vector size, and we can call that n for this one. The second for loop is dependent on the size of each string that we're looking at, So we can call that variable m. And then we have erase functions. Erase functions also have linear dependency in the number of characters that they're removing. Since we're removing potentially several characters, it's going to be linear in that situation as well. As a result, this thing has a time complexity of big O of n for the vector size, times m for the number of characters in the string we're comparing to, times, say, O for the number of characters we're erasing from the prefix string. So in terms of time complexity, this is not an optimal answer, but in terms of space complexity, since we're only creating a string, it's quite good in terms of space. And since these only can go to 200, it should be able to pass muster. So let's look at the rankings here. For the test cases it runs fairly quickly. Now with the short length of the vector and the strings, this distribution here could indicate that the strings and the vector aren't long enough to be able to effectively differentiate between various solutions with different time complexities, since they're all packed in quite close to each other. It could also mean that there isn't too much variation in terms of big O solutions. You don't have a, say, an m times n times O solution and a big O of n solution, for example. So that's what this distribution could mean. In terms of memory, we're all bunched into this distribution here, so not too surprising to be pretty good on memory usage. And this larger memory usage indicates that there can be ways that you can take more space for some other solutions, because I'd expect to be able to ping pong around this area a bit, but not from here, say, all the way down to here. That was one solution, setting the prefix to a string and then chopping it away till you get your final answer. Now we're going to go ahead and start planning out the second of the solutions. So instead of erase, let's just reset this. We're going to use concatenation and go forward instead of in reverse. Now for building up the prefix from nothing, we're going to have a few additional variables. One, we want to have a string to house the one that we're currently comparing to. We need to have our string that houses the prefix, like before. We also need to have a character variable to house the character that's going to need to be added to that prefix to build it up. After those variables, the first thing we want to do is go through the vector of strings and find the shortest possible string that is present in that vector. Now, of course, if we find an empty string, we can just immediately stop what we're doing and return the empty string, since that's the longest common prefix. But otherwise, we're going to go through the strings, compare sizes, and make sure at the end that our comparison string is set to the shortest possible string present. That's going to minimize the number of iterations in the next loop that we do. And that loop is also going to be a nested one, and it's going to first go through that comparison string. So we're looking at each character in that comparison string, and we're also going to have an inner loop that looks at each character in the strings of the vector. So it'll look like this for this example here. At the end of that for loop, flow is going to be the string to compare. So what we want to do is that for each character in flow, we want to look at the corresponding letter for each string in the vector and see if they match. If they do, great. We know at the end of that inner loop that character is present in every string, thus that character can be added to build up our prefix. And the way we do that is by string concatenation. So we'll just set our prefix to itself plus the character to add. As soon as we find a mismatch, we can immediately return our prefix. And then if we get through the entire for loops, we can also afterward return our prefix. So let's look at that code. Here are the variables that I was talking about. This time we have two strings. The string to compare is one of them, and I've set that equal to the first string that's present in the vector, much like prefix was in the previous answer. However, now the prefix string is set to empty. Finally, a character variable is present, and I just named it character to add, or char to add. Now the first for loop is going to come in, and the purpose of this for loop is to search the vector for the shortest string. There are also comments here that foreshadow the second for loop coming in, but this one is first going to go from the second string in the vector to the end of the vector, and the first thing it's going to do is, if at any point it finds an empty string, i.e. strings I.size is equal to 0, well, then our job is complete. We just return an empty string and we don't have to do anything else. If that never occurs, then the second thing we do is look at the sizes of the string to compare and the string that we're currently looking at. If our comparison string has a bigger size than the other one, well, we want to find the shortest one, so we're going to set string to compare to whatever that string is. And at the end of this loop, we either have immediately found our answer being an empty string, or our comparison string that we're going to use for the second loop here is going to have the shortest possible length to it, which minimizes the number of iterations that this loop we're going to create is going to have to do. Next, as this comment suggests, we want to go through each letter in the comparison string. So our first for loop is going to go through the string to compare size. Start at the beginning, end at the end of string to compare, and of course do stuff in it. And as this second comment suggests, we immediately go into a second for loop. And for each letter in the comparison string, we want to look at the same letter position for each string in the vector. So this for loop is going to go from j is equal to 0 to the end of the vector size, because we want to look at each string in that vector. Now we get to the stuff to do. Within the second for loop, we want to first look to see, do we have a mismatch? If that letter in the comparison string does not equal the letter in the string that we're looking at, and in this case, to get that specific letter, we need to call the vector, we need to indicate which string we're looking at, which is the j value here, and we then need to say, hey, you told me which string you want to look at, which letter in that string you want to look at, and that is I here. So if those aren't the same, we found a mismatch, we immediately return prefix. If it is a match, however, we want to continue on our merry way until we get to the end. And if along this loop we've gone through each string in the vector, looked at that letter in the same position, and they all match, once we get to the end of the vector, when j is equal to the string size -1, we definitively know that that character is present in all the strings, and it should be added to the prefix. But we need a way to record what that character is. That's where this character to add variable comes into play. So we set that variable to equal whatever that letter is. Now, outside of this for loop here, we are going to use string concatenation to add that character to our prefix string via the plus equals operator. So it's going to set a prefix to itself plus the character to add. And if you're asking, well, why can't we just directly say that prefix should be equal to itself plus strings ji? Well, that doesn't work because, remember, we're outside of this inner for loop. We're still within the outer for loop, but this outer for loop has no idea what j is, so we can't reference j outside of this inner for loop, which is why we plop it into the character to add variable and then use that to add to the prefix. The final thing to do is, outside of the entire loop here, we simply return the prefix. So these loops are going to go until either we get a mismatch, and at that point our prefix should be correct and we can immediately return it, or we get through the entire loop set, our prefix should still be correct, and thus we should still return it. And with that, this should be the completed code for the second method. So let's run that and see if we get red text, which we didn't. This works. The custom test case here, let's say eliminate that like we did in the previous one and see what happens. It should, after much judging, get our empty string here because of this line that's present, and this should work. So fingers crossed, hit the blue button and hope for green, which is what we get. Now, before we click to see our rankings, let's see how the time and space complexities have changed. Now, our space complexity, technically the memory that we are utilizing has gone up. We have more variables here. We have a bit of a constant space usage with our character variable here, and we now have two variables with the two strings. The string to compare functions kind of like the prefix did in our previous solution, where it's eventually going to equal the shortest string that's present in the vector. This can range from being empty to essentially being whatever the first one present is. But eventually it's getting to equal the shortest string. Prefix initially is empty, but it's of course eventually going to equal the size of whatever the longest common prefix is. So we can call the shortest string in the vector n, we can call the longest common prefix variable m. This algorithm is going to have a complexity of big O of n plus m, whereas in the previous one it had a space complexity of just big O of n. So we've increased our space complexity. However, let's look at how our time complexity has changed. Here, our for loop is going to be dependent on the vector size. And while it could potentially exit early, in worst case scenario, it has to go through the entire vector. So best case, it can only run once, or it can run the entire length of the vector size. So looking at worst case scenario, we can say this one has a time complexity of big O of n, where n is equal to the vector size. For this nested loop here, we have the outer loop that is dependent on the string to compare's size. But at least for this dependency, this for loop ensures that that string is going to be the shortest it could possibly be. So this for loop helps optimize and minimize the number of iterations that this for loop is going to have to go through. Now this inner for loop here is much like this one, dependent on the vector size. And again, it could potentially end early if we see a mismatch as soon as it starts, or it could potentially have to run the full length of it. So in the worst case scenario, full length of the vector is the maximum size. It's dependent on that. So far we have, say, string to compare's size, we can call m. The vector size we're calling n. So we have an m times n dependency here. Now we have to add in the string concatenation, and that one is linear in the string length. However, unlike the previous solution, this concatenation is not within the inner for loop. It's still nested in the outer for loop, but because of that, you don't have a multiplicative effect with the inner for loop. So this is just an additive one. So this one is going to have a time complexity of big O of m times n plus big O of m times, say, O for the string concatenation. And that additive dependency is better than that multiplicative dependency that the previous solution has. So we've increased our space complexity a bit, but we've reduced our time complexity with this solution. However, again, because of the small nature of the constraints here, it might not show up in the rankings, which we'll see. Okay, we've bumped up here, which in terms of our complexity would make sense, but I've seen it ping pong around, so essentially the rankings can't really differentiate this solution from the previous solution reliably. And memory usage, see here, we have a higher percentage score. We're higher up in the rankings for our memory, but we know we're utilizing a bit more memory than our previous solution, so we should probably be lower, not higher. But again, due to the ping-ponging nature, it kind of bounces around here. So for the constraints and whatever test cases that they have here, this method and the previous method can't really be effectively differentiated based on the rankings, which is why doing time and space complexity analysis is always a good thing. Okay, that was how to solve the longest common prefix on the LeetCode website. I hope you got something out of this video. If you did, consider subscribing. I do these types of videos twice a week. And as always, I will wish you happy coding and have a nice day.